Hello everyone, my name is Wonderful Shama Kaitani and I'll be presenting rehabilitation hand volume control based on computer vision. First of all, rehabilitation is the process of returning to a healthy and good form of life through training and therapy. Now, with traditional rehabilitation methods, patients are required to move from the comfort of their home all the way to hospital centers, lining up to have a doctor's appointment for these same rehabilitation exercises. And to combat that, as it seems to be a challenge to always move from their home to these hospital centers or wherever they have been allocated. To do this, we have proposed a system whereby one can stay at their home and only use a webcam to have rehabilitation exercises and in specific hand therapy. This implementation uses the webcam or a Kinect system, and it translates a patient's hand stretch levels to volume of the system, which is displayed on the display output of the system as well. Moving on further to that, we have the proposed methodology, and the system uses the multimedia development lifecycle, which moves in 6 steps. Firstly is the concept of what we want to do. We have to first define what the system is to do, and in this case, it is to replace the traditional methods and provide a more convenient way of our patients to have hand therapy at the comfort of their home without having to travel. Secondly, we have the design, of which we'll talk about later, and then it moves on further to collecting materials, assembling, testing the system if it works, and if it is perfect enough, distributing it and sending it out. Now, coming to the design of the system, it uses OpenCV, which is a library for programming functions, and MediaPipe, which is a cross-platform framework for machine learning. If we come on to the flowchart of the system operation, firstly, when the system starts, it initializes the program and then starts a video live stream as the one you can see below. Once it starts the video live stream, it has to detect a hand and whether there is motion. Once correctly detecting the motion and the hand, it has to also detect the index finger points and the thumb points. And if it correctly detects these thumb points and the index finger point, it moves on to capturing the current frame and translating that to volume. And once it captures the volume, it changes the volume of the system accordingly based on the patient's hand stretch lengths, and then it ends the program upon completion. Moving on further to that, also we have OpenCV gesture detection, and we use MediaPipe in this case for the gesture detection. And we use MediaPipe as it has designated 21 points, which are shown on the screen once the program is initialized. And we use 2 specific points of the index and the thumb, the index finger and the thumb, which are to help us control the volume of the system with the help of Pyco. Now, coming down to our integrated modules. We have NumPy, which is a library for the programming languages, and we have Pyco, which is Python audio control library in full, and is responsible for controlling the system's audio via the running Python codes. And we come down to material collecting, which is stage 3 of the MDLC, which is the multimedia development lifecycle. We have the patient's hand, the webcam, and the ruler in between. This is set up so that we can find out the accuracy of the system correctly, and we, from our findings, we found out that from 30 centimeters away from the camera, we achieve 100% accuracy of the system, and as we go further away from the camera, the accuracy drops. We use this so as we just have a clear picture that when we send it out to our patients, they know exactly how to use this. And when we come down to our assembly, our software and hardware implementation, we implemented the system using Python and PyCharm. Python 3.7 has proved to be the best running version on the system, and it was so smooth. And we use PyCharm, which is a software which runs these Python codes. We also run the system on a Windows 10 system, but it's cross-platformed and it can run on any operating system. As for the hardware implementation, we use the Kinect camera or any other normal webcam. For the simulation experiment, we can see here a series of pictures which show the key differences between the index finger and the thumb. And if it is very close together, above 1 centimeter, it gives us 0% on the screen from the first picture. And when we increase, it goes to 31, 74, and so on and so forth. And here is the same illustration of how the experiment works. If we stretch our hand all the way up, it goes up to 100%, and it gives this information to the doctor that our patient is able to fully stretch their hand. And if the patient is not able to fully stretch and maybe stretches that little, it goes to about 51%. On the far right, it shows how much our program is able to change the operating system's volume accordingly. And here is a video example of how much a video simulation of the system in progress. So we can see that even if we have two hands, the system only picks one hand so as the patient can focus on one hand in exercising, and not only two, as it will bring interferences. And so you can see on the far right that shows percentages, and in this case we have the percentage, which is the volume, and FPS. FPS refers to the frames per second, and it's defined at the rate at which different single pictures put together form a video in the screen. And in short, it's a description of how best and how smooth a video is running. Now, moving on further to that, we have a graph here which shows us the stretch length against the volume. And as we already discussed, this is based off on the index finger point and the thumb point. So if it is about 13 centimeters apart with the stretch, it gives us 100% accuracy. And if it goes a bit down and all the way down to about 1 centimeter or less than 2 centimeters, it goes down to 0% volume translation. Here is also another graph which shows the camera accuracy against the patient's distance from the camera. And we can see that at 30 centimeters away from the camera, we have 100% accuracy. And if we move further away from the camera, about 104 centimeters, it won't give us correct readings or none at all. Moving on further to that, as a conclusion, we can also say that upon testing the system, we have reviewed it to be very user-friendly, as it is all plug-in and play and requires no experience of usage. The system provides an alternative to physical interaction, as there is no need of a patient to travel all the way to these physical locations each and every time they want to have rehabilitation or hand therapy. The system is very interactive and engaging, as you can spend so much time on it and not feel stressed. And the accuracy of the results is unfortunately based off on how close the subject is to the webcam. Now, for the future plans are to produce more accurate readings from the webcam and the system by calibrating it with each user, as the size of the hands might differ, and like scaling the project and placeholding it as a full-time rehabilitation aid, and develop it into a fully functional system which can be easily calibrated to suit different rehabilitation patients. Thank you very much, and that is all from me.